Hello everyone, I'm Samuel Chen from Wells Fargo Bank. Today I'm going to present our work on the learning to program variational quantum circuit with fast weights. So this is the agenda of my talk. So I will introduce the idea of fast weight programmers, and then I will extend the idea to the quantum regime, and I will show two use cases. One is the sequence learning, and the other is the reinforcement learning. Okay, so there are two major technology breakthroughs in the past couple of years. So the one is the AI and the machine learning. I believe most of you are very familiar in, for example, the reinforcement learning, AlphaGo, and all those transformer-based models that probably you are already using every day. And the other trend is the quantum computing. So although the quantum computing theory is being developed since the 1990s, but the hardware advancements are mostly after 2017. And there are several vendors out there, for example, IBM, Google, D-Wave, or others. So theoretically, the quantum computers can solve certain kind of tasks which can outperform the classical computers. But existing quantum computers are quite noisy, and they are not error corrected, so you cannot run very deep circuit or very a circuit with a lot of qubits. So there are a special kind of quantum circuits called variational quantum circuit. They are developed for the near-term quantum computers, and these kind of circuits have been shown that they can succeed in the quantum recurrent neural network, quantum reinforcement learning, and sequential learning. But there are some challenges there. So when you do the gradients of a recurrent neural network, such as the LSTM, you need to do the backpropagation-through-time, right? So you need to unfold the computational graph along the time, and you need to calculate the gradients across the time axis. And this issue is still there in the quantum recurrent neural network. So there are different kinds of ways to try to tackle this challenge. So the idea of fast weight programmer is that, so the neural networks, they have weights, and the weights are actually the programs of that particular machine. So the neural network is a machine. You have some connections, and the weights are actually the programs, right? So the weights decide the task that can be solved by this neural network. So the programmers means that a neural network which can change or update the weights of another neural network. So in the fast weight programmers, we have two neural networks. The first is the slow programmer. The slow programmer is, the idea of slow programmer is that this neural network is trained by the conventional gradient descent method, or you can use other evolutionary methods such as the neural evolution. And the fast programmer, another neural network, this neural network is, so we don't calculate the gradients of that fast programmers. The fast programmer is being programmed by the output of the slow programmer. So the slow programmer learns to generate the changes or updates of other neural network. So for example, in the original form by the Professor Schmidt-Huber, their group designed this original classical fast weight programmer. So the slow programmer can generate the difference of the network for each of the connections. But the original form of the fast weight programmer suffers from some issues, because if you have a very large fast programmers, then you need to have a slow programmer with a lot of output nodes. And so, we can extend the idea of the classical fast-way programmer to the quantum fast-way programmer. But I need to provide some background of the quantum machine learning. So in the quantum machine learning, there are different categories. So the CC is using classical data and the classical algorithm. So this is not the quantum machine learning, but we can consider the classical data and the quantum algorithm. So this is the most active field that we are studying today, because most of the data we have are classical. And QC means that you are using classical machine learning to solve quantum physics tasks. So probably some of the physics-informed neural networks fit in this area. Or for example, the field that you use classical convolutional neural network to learn how the quantum phase transition occurs. And the final one, the QQ, means that you have quantum data and the quantum algorithm. So here the quantum data may be from the quantum sensor. So you have a very sophisticated sensor, and it can sense the environment, and the result from the sensor is a quantum state. So you want to define a particular kind of quantum circuit which can be used to classify or reconstruct the information from the quantum information. So of course, this is the most difficult field, because we are not yet, we don't understand both fields, right? So today I will focus on the classical data and the quantum algorithms. And for quantum machine learning, we have something that is very, very similar to the classical neural networks that we already studied for quite a while. So it's called the variational quantum circuit, or it is also known as the parameterized quantum circuit. So this is a kind of quantum circuit with tunable or learnable or trainable parameters. So we try to train the parameters by the method that we already developed in the classical machine learning. So for a variational quantum circuit to process the classical data, we have the three components. The first is the encoding circuit, the U of X. So you have your pixels, your speech signals, your embedded tokens. You need a particular kind of circuit to transform your information into a quantum state. And then the quantum state will go through the variational circuit, the V of theta. The theta here is a set of parameters. Usually they are the rotation angles of those quantum gates. So these zetas are our learning target. And finally, we measure or extract the information from the quantum circuit, because if we want to do the inference, if we want to further process the information from the quantum system, then we must measure the system, and we get those values, for example, those floating point values, so that we can use another, for example, classical neural network transformer, or probably encode again this information into another variational quantum circuit to do further processing. So now we have the quantum machine learning with this kind of structure. So some of the computational tests can be divided into two parts. So if a particular subtask can be solved by a quantum computer with some advantage, then we will use a quantum computer to run that part. And then we have the classical computer. So for example, we measure the information from the quantum computer, quantum circuit, and then we can use the classical computer to, for example, evaluate the gradients and calculate how we update the quantum circuits, and then we feed back to the quantum system. Because now it's very, very difficult to calculate the gradient directly on a quantum computer. And it can be shown that the gradients of a particular quantum function on a particular quantum rotation parameter and a particular data point can be derived by running the circuit twice with some slightly different parameters. So this is called the parameter shift rule because you run two circuits with a shift of the parameters. So once we know how to calculate the quantum functions, we can connect different nodes. For example, the quantum circuits, the classical neural networks, tensor networks, and any kind of classical functions that you can imagine into a directly acyclic graph, and we can build a very sophisticated models, and we can train the whole model end to end. So, for example, you can use PyTorch to wrap both the quantum circuits and the classical neural networks in a single PyTorch module, right? And then you calculate the loss, and then do the loss dot backover. So all those gradient calculation, both the classical neural network and the quantum neural network will be done under the hood. But the mentioned method is with a particular challenge, right? Because calculating the gradients of a quantum circuit is very expensive. So for a particular data point and a per parameter, you need to run the circuit twice. So you cannot imagine that you can use this kind of method to develop a quantum model with millions or even billions of parameters that the classical neural networks are very good at. So in the quantum fast array programmer, this is the first of its kind that using a classical neural network without any recurrence to change the quantum circuit parameter real time. And we also want to tackle a particular challenge that we don't want the neural network to scale too quickly when we have a bigger quantum neural network. So how we design the model? So we design the quantum circuit like this. So once we encode the quantum circuit, it will go through several layers of the variational blocks. So in the dashed boxes. And so we can have multiple blocks to increase the number of parameters such as the expressibility of the circuits. And then we use a classical neural network. So first we have an encoder, which is encode the information, the input information. And then we use two separate neural networks. One neural network to generate a vector with the length equal to the number of layers or the number of blocks. And the other with a length equal to the number of qubits. So if we do the outer product of the two vector, then we can have the parameter changes of all the quantum circuit parameters. So the idea is this. So we have this. This is the generic diagram, and this is the actual detail of the quantum circuit. So in each of the small boxes here, they have several control gate and a parameterized gate, as shown in the red boxes. And the data encoding part here is fixed. So you have a fixed rotation gates, and you put in your input information. So I will introduce two examples. The first is the sequence learning. So originally, people used the classical LSTM to learn the sequence. You have sequence-to-sequence model or other discriminative or generative model. But the original neural network suffers from some vanishing gradient problem, so there's the LSTM. And we further improved the LSTM into the quantum LSTM by replacing all the classical neural networks variational quantum circuit. We can show that the quantum LSTM can use a smaller number of training epochs to reach the optimal solution. However, training quantum LSTM is very expensive, so we use the quantum phase wave programmer that I just showed to do the similar task. And the training setting is that, okay, we have some time series. For example, we have 4 data points, and we want to predict the next one. And we use the damp simple harmonic motion and the Basel functions. Those are very basic equations in the physical science, and a nonlinear autoregressive moving average equation to generate a nonlinear time series. And we can show that, okay, so for the quantum phase wave programmers, we can reach the performance very similar to the quantum LSTM, but the training is much faster, and we don't have any recurrent connections here. And you can see that even the single epoch of training, it can basically capture the form of the function. And this is the same in the Basel functions. And the more challenging the NAMA sequence, so the NAMA 5 and NAMA 10, the 5 and 10 means that they have different nonlinearity. And the final use case is the reinforcement learning. So in the reinforcement learning, we have an agent, right? And the agent learns how to make decisions by interacting with the environment and learns through trial and error. So here, we use our hybrid quantum phase wave programmers to process the information that the agent gets from the environment. So here is the actual model. So this is very similar to the one that we use in the for the time series modeling. The only difference is that we add 2 small neural nets, very small, just a couple of parameters at the end of the quantum circuit. Because we are doing the actor critical learning, so we need to generate the action logics and the state value. We also compare the model with quantum LSTM with different number of variational quantum circuit layers. The testing environment is this. So this is a simple navigation task. So if you are not from the quantum machine learning field, that even these kind of tasks are still very challenging in the quantum reinforcement learning. So this is the environment that we use, and know that the environment has 147 dimensional vector as the input or the observation. And the agent need to decide the actions that it will take. Okay, so this is the last slide. So we test on the 2 different environments, and probably, I mean, you can see the paper because this is not very clear, but you can see that the quantum phase wave programmers are the 2 best performing agents. So you can reach the performance of quantum recurrent neural network without any recurrent connections. So the training is much faster, and also it is very stable when it reaches the optimal score. So conclusion, so classical neural networks can be trained to generate the updates or the changes of the quantum circuit parameters. And even without recurrent connections, the quantum phase wave programmers can reach comparable performance with quantum LSTM. And potentially, we can use recurrent neural network, classical recurrent neural network, or transformer-based models as the slow programmer to program the variational quantum circuit. And the codes and the papers, and feel free to send an email to me, or we can talk during the conferences if you have any questions or if you are interested in this work. Thank you.